we will continue lecture 3 on covering ordered sets and fields, supernums and phenums, and the least upper bound property. To try to understand. And lecture 4 will continue that. So an ordered set, that's field. An ordered set is a set S with a relation which we call this, such that for all x and y and in S, either it's x is equal to y, x is less than y. Now this is a relation, so this is relation. So this is relation. I will tell you what I mean relation. So this is 1. This must be one of the 3 things. And number 2. If x is less than y and y is less than z, x is less than z. Transitivity. So here are 2 examples. Oh, there are actually 3. This one. Oh yeah, the last one is a bit more weirder. So these, we could just define something in here. M is less than M if N minus M is in the naturals. Showing that the naturals doesn't have 0. Oh god. Q is less than R if there exists an M such that R minus Q equals to M divided by N. So there's not going to be any negative numbers, so that's good. So these are the 2 basic examples of ordered sets, and the final one one's a dictionary ordering of the rationals. Now what does this mean? Well, basically when A dictionary ordering B, then this is the set A, B, or ordered pairs. A is in A, B is in B. So now we say AB is less than QR if either A is Q or A equals to Q and B is less than R. So for example, 1, 2, 1, 3. So B is less than R and A is equal to Q. So it's either this situation or this situation. If this is not less than, then they're equal. If this is greater, then it's not less than. And the equals probably when both of them are equal, so in this situation, this works. Then this is an ordered set. So let S be an ordered set and let set E be a subset of S. If there exists a B in S such that for all x in E, x is less than or equal to B, then we say E is bounded above and is an upper bound for E. So what does this mean? Well, here again, if there exists a B in S such that for all x in E, x is less than or equal to B, what? Okay, this might be reverse intuition. But right now, do not give me copyright, MIT, please. I'm checking something. Lecture 4. Oh, lecture 3. Like, something is wrong.
You can always check whether two elements are bigger than, namely that for the usual ordering, it's not bigger than the other. Check the next letter, or let me define what I mean by this least upper bound. I remove that from such that
for all x in E,
x is less than or equal to B. So here I have this order less than or equal to means just what it means in English. Either x is less than B or x is equal to B. Same thing with bigger than or equal to, and so on. But just keep in mind that
if there exists a B in S such that x is less or equal to B,
order is bounded above.
So this kind of makes no sense intuitively. It's kind of the opposite. It's so basically it's saying for all elements and for any element in S such that for all x in E, if there exists an element in S such that x is in E and x in and x is less than or equal to B, then we say E is bounded above. And B is an upper bound for E. I know. So it's an upper bound. So this is E This is upper bound. Don't worry, we'll get examples. Because these definitions can get confusing. Trust me, even right now I was confused like 2 minutes ago what was going on. Then we say E is bounded below and B so as you can see, we're trying to get LUBP and understand what that means. We already understand the ordered set. Your ordered fields are going to get better. And finally, we call it B0 to S is the least upper bound for E if B0 is the upper bound for E, and if say B is an upper bound for E, then B0 is less than or equal to B. So it is the least upper bound. There are a bunch of upper bounds that are infinite. But say this is the least possible one. And we also call the B0 the supernum of E, which is where we get supernums and infimums. And B0 is the greatest lower bound for E. If B0 is a lower bound for E and if B is any lower bound, then B is less than or equal to B0. So all lower bounds are less than or equal to. So now in this situation, B0 is infimum E So, say we have this set -1, 0, 2 upper bounds 2, 3, 4, 5, and the supernum. Oh yeah, by the way, the set is E, set E. So the supernum E is 2. Because that's the least one. That's the least possible one. And then the lower bounds are -1, -2, -3, and the inf E -1. Nice to know that. Another example. Okay. So E So the upper bounds are 1, 3, 2, 4, 5, 7, 6, more and more, dot, dot, dot. Lower bounds. Oh, and the soup. Not even going to put E at this point. Actually, fine, I'll put E. 1, LB, 0, -1, -2, and inf E0. But hey, do you want an example where The supernum and the infiniums are actually not in the set. Well, we'll define the basically the same set. But no greater than or equal to. It's just greater. It's just greater than. It's just greater than. It's not equal to. So, but still, the supernum and the infinitum are the same. It's 1. Okay, well, what are zero arc elements? So, definition. An ordered set S has the least upper bound property if every E in S, which is not empty, and bounded above, has a supernum in S. E.g., so basically every subset E, which is in S, is non-empty and bounded above, which is not and bounded above, has a supernum in S. So not all subsets, just the subtypes which are not empty and bounded above, has a supernum. If it's bounded below, I think it might be infinitum later. I'm not sure. So we got LUBP. So LUBP might be hard to describe. E is 0, 1. So we take all the subsets except the empty set, not empty. Soup. 0 is in S, 1 which is in S, 1 which is in S, and here if E is in S, E non-empty, then negative E, negative X is in E. So this is not, so we're just denoting negative E by this, which is in N, by the well-ordered property of N. There exists in M such in E such that M is for all is M is less So, basically what we were just trying to do here is that if M, so negative M is the supernum of E, wait, yeah, negative, is it your negative E? Well, Z has the least upper bound property, LUBP. Q doesn't have the least upper bound property, and if you want to see the proof for that, you can watch Real Analysis, Lecture 3 around the end, and it also includes part of Lecture 4. So Q does not have LUBP. That separates Q from the real numbers, the rationals from the reals. So we will continue describing R in the next lecture. but we were trying to describe R. That's what we were trying to do this entire time. So anyway, bye.